So the exam is be a little bit with each chapter plus 3 problems to solve. And of course, the graduate students will have slightly harder problems than the undergrads, but we'll have all those done. Okay, so but today we're going to do again strategy on looking at problems that we have. In particular, it's chapter 8 problem. We're going to start with 8.1. I think it's 8.1. Doesn't look like 8.1. But again, we're going to go through the strategies here and hopefully not do any bad math, and we'll see what happens. All right, so what I'm going to do is I'm going to share my screen. And it's Chrome. That one. So this one is the one that should be shared here. I'm going to move the other 2 screens off to the side here. Okay, so let me see if I can get this bigger. Okay, so this should be the same in your book if you have chapter 8. If you don't have chapter 8, go ahead and just use these. Mine actually doesn't have this one in it, so we'll see right here. All right, so the first thing we notice is the mass spec. So if you want to unmute and just talk through it, kind of what we see.
I don't think we can see it right now. I just see like a white strip in the middle.
Okay, let me stop share and reshare. Okay, minus it. Okay. Okay, stop share, reshare. Okay, can you see it now?
Yeah.
The full thing, not like just a strip. All right.
Yeah, the whole thing.
All right, let me see if it's still there. I'm trying to move it so I can look at the camera while I'm doing this, but if is that still sharing correctly?
Yes.
All right, excellent. All right, so the first thing we notice on this is, let's start with the mass spec. We actually have 2 different mass specs. We have our regular electron impact ionization. And so, of course, we're going to have, obviously, there's some functional group that decomposes rapidly. So we actually are going to do chemical ionization with methane to try to get that parent ion peak. So what's the key phrase when we use chemical ionization with methane here? We're going to get our parent ion mass only, or
don't we get the parent ion plus a methyl group? Yeah, correct. Plus 16.
Plus a methyl group, so that's plus 16. So we're looking for mass plus 16. And so we actually still have in both the electron impact and in the chemical ionization, we have something anomalous. We have an odd number. So what does that tell us right away?
Nitrogen.
We probably have 1, 3, or 5 nitrogens. 1, 3, or 5 nitrogens right here. And if we look at our, we have 193 and 197. Those don't seem to be an isotope ratio there. They seem to be a little too small for that. So what do we have as our parent ion mass peak here? Just calculating our parent ion mass peak, what do you think you get? Okay, so it's going to be the masses in the chemical ionization peaks, but that's going to be that peak minus our methane group, which is 16. So it looks like we're getting something like a 181 and a 179 for those. And then we also have 2 other peaks there, the 171 and the 169. Okay, so those are important to take a look at when we're comparing the 2 peaks. Obviously, we have some functional group that is easily blown apart by the electron impact. Okay, so we have nitrogen, we have a mass of 181 as our starting point. And so we have something to look at there. Okay. Let's go on and look at our IR here. Ooh, interesting. No carbonyls, but a huge peak at 2877. So that's 2900. So, and nothing here. So we're looking at something completely aliphatic. We're nothing above 1500 here. So we have completely aliphatic carbon-carbon bonds, but we have this broad peak here, okay? So it's not two peaks, and it's not as broad as an OH peak. So what's that suggesting to us right there?
Primary amine?
Yeah, primary amine, because we don't have a carbonyl, so it can't be an amide. And so that's really a pretty good suggestion there. And we only have aliphatic hydrogens. Okay, so we have nitrogen. We might have a primary amine. We have 181 molecular weight. That's pretty high for an aliphatic compound. So that means it must be some kind of, big or long chain. Okay, there we go. So if we look at our Proton Nmr, we have a big, huge mess centered around 3.8 to 3.4. Okay, so and that big, huge mess is all the protons, and maybe this is one or more protons over here that's slightly different here. So what does this suggest to you?
But it's not symmetric?
That it's not symmetric, or everything is like right next to a heteroatom. Okay, can you see am I still sharing my screen? Oh, it says it's paused. It says my screen is paused. Why is my screen paused? All right, can you see the MR now? Okay, I don't know why it paused my screen. Maybe it's because it doesn't like my internet or something. Okay, so we have this big, huge, massive peak here. So that's suggesting to me we have maybe something that's alternating, that has only one kind of aliphatic hydrogen, but they're all kind of different somehow. Okay, so if I can do it without pausing, let's look at the proton of the carbon NMR. All right, and so everything is below 77. So this is a weird peak here at 77. It's really big and strong. What is that? Solvent, that's right. And which solvent in particular? So yeah, this is a deuterochloroform. So that means everything else is below that. So we're looking at something around 42, and then a 60, and then 1, 2, 3, 4 peaks up around 70. So all of these carbons are attached to at least one heteroatom, and these might be attached to 2 heteroatoms because they're shifted so high up. Now notice all of these are down. So what does that suggest? Okay, when in doubt, that line is the 123. Ring, well, in the depth experiment, that's actually suggesting something else. Right, okay, Marvin's got it. They're all CH2s. Odds are up, evens are down. And so they're all CH2s. So we have 1, 2, 3, 4, 5, 6 types of CH2s. And I agree with Iran that they're in a ring because we have this weird chunky thing, okay? And a lot of, at least 3 of the 4 of these carbons here look like they have some kind of maybe a methylene CH2 with a heteroatom on either side. Okay, that's why they're shifted so far higher than everything else. And then maybe something with only 1 on 1. So maybe these only have 1. So we have a methylene bridge here. Okay, so that being said, our only major fragment here is 45. So, oh gosh, 45. Again, I don't remember these things. 45 is a CH2 OH or a C2OCH3. Okay, so, and again, that's our only fragment. We don't have any nitrogen fragments showing up. 63 is not a common fragment. 75 is common fragment, but it typically has sulfur in it. So, all right, so we have some kind of system that has that. So let's go back to our molecular weight, figure out how many, well, we already know how many types of carbon we have. We have 1, 2, 3, 4, 5, 6 types of carbon, but it looks like we have more than 6 carbons here. So what kind of empirical formula should we start with here? So is it going to be, let's see, we have, can it have chlorine? Maybe chlorine here. Let me see if I can blow this up without freezing it. That could be a chlorine there. Now, what we'd see for a chlorine is we'd see a loss of 35. And if we go from here to here, we have a loss of 30, a loss of 32. And we have a loss of 26 here. We have a loss of 26 there. We don't seem to have anything that correlates to a loss of 35. You'd expect that chlorine to come off like that, but it's definitely possible. And that might account for one of these 2 peaks here being lower than the others. Okay. So let's see, what else do we have? We have an empirical formula starting out with C13. Let's see. And I'm using the 181 as the upper number here.
So why are you using 181?
Because in the chemical ionization here, in the chemical ionization using methane, if we look at our common fragments there, when we have chemical ionization, we typically see it plus a methane or plus a, let's see, oh, it's a plus an 18. It's a +1 or plus 18 are the common ones. Okay, so that's the methane fragment that's attaching to it. And so we have the difference of here of this to this is that the 18 peak I'm looking for? 197 minus 171 is equal to 26. And 26 is 20, that's a different number there. Okay. So that's a loss of like two carbons. So this, let me see. So it's not 181, it's 197 minus 18. So it'd be a 179 peak. Might be a parent ion peak here because of the chemical ionization. And this does look like the 2/3, 1/3 peak right here. This 169, 179. So there is some evidence for the chlorine being on that right there as well. Both this ratio here and the shifts here in the carbon NMR. Okay, so let me look for. We definitely have some kind of aliphatic system in there. And it has a mean. It might have an OH, but it definitely has if this is chlorine, that also gives us our odd peak. And then that would turn this into an OH peak here. So we have oxygens and OHs. So if we take the highest peak and do a minus 19 on it, sorry, minus 18, to give us our empirical formula for that chemical ionization peak, minus 18, that's 179. And minus 35 would give us a 144 as a starting number. The reason I subtracted 35 from it is, well, there might be one chlorine there. And so that'll get us down to carbons and hydrogens and oxygens at that point.
So if we are subtracting methane group from the parent ion peak, like to obtaining the parent ion peak, so isn't it should be 16 instead of 18?
When you ionize methane in the system, it actually has hydrogens come off, and therefore you end up with a plus 18 peak. So those hydrogens are also found there. You would, you know, because let me see. Yeah, because if you look at the decomposition, it does that plus 18 peak with ammonia ions. Okay, it should be the plus 15 peak then, yeah, for methane. Yeah, it's plus 15 for methane. You are correct. I looked at the wrong table. So 179 minus 15 is equal to 182. And that gives us minus 35 if it has chlorine in it, which is a 147. And we know we have at least 6 types of carbon. And if we have a chlorine on here, then we don't have nitrogen, and this turns into an alcohol.
What table were you looking at for the
plus 18?
Yes.
The plus 18 was found on table 1.1. It's ions formed are the plus 1 and the plus 18, but it depends on the thing you're using to ionize it. If you go back to section 1.3.1.2, if you use methane, you get a plus 15 peak. If you use ethane, you get a plus 24 peak. If you use ammonium, you get the plus 18 peak. So, so that's why I accidentally chose the plus 18 as the table 1.1 when methane should give us a plus 15 and a plus 1. So 179, 97 minus 15 is equal to 182. So that's where that chemical ionization peak, well, that's why that one peak's higher than the others. And it looks like we lose a fragment and we still have chlorine on the system. So the fragment we're losing is that 197 minus 171 is equal to a 26, which is, of course, 13 plus 13, which is a CH2, C2H2. So that would account for that mass loss there as a C2H2. And that would give us the fragment that we have on there. But notice that when we lose that C2H2, we still have a chlorine on there. So if we look at common fragments lost, a 26 is a C2H2 or a C2N.
So I want to add one thing. I was reading through the chemical ionization from the chapter 1. And they were saying that the base peak in the CI region is close to the parent peak instead of the highest one. So if you read through that page, they were saying that M+1 is the parent peak.
So that's the parent peak or the base peak? Like
the base peak is M+1.
So that suggesting that the 169 is the
yes.
M+1 peak?
Yes, and 168 is the parent peak. And the rest, that 195 and 197 is there is a presence of ethylene or the propylene that added to the base peak, and it's created 195, 197.
That's okay. Excellent. Excellent. So that means our 169 looks like our parent ion peak. And assuming the ratio still is the 2:1, which it looks like it is, I think we still have chlorine on there. So we have 169 minus 35.
It go for 168 minus 35.
Oh, 168.
Because
so that gives us 133 as our base one, which is, of course, so that would be 13, goes into that 10 times with a, so C10H13 is our starting empirical formula. Plus chlorine, CN. Oops. Oops. Hold it. Where is that? Where'd my screen go? Okay, hang on. This is okay, I don't know where my screen went here. Oh, that's the bonus problems, that's why. Okay. All right, so, gosh, I need to find my thing again. Okay, where did that go? Okay. Bonus problems. Okay, I think I've got this back again. I'm going to share it again. All right, can we see the problem again? Okay. All right, so now we're using chemical ionization. We've now figured out that our base peak is our M+1 peak at 169, which gives us a molecular ion peak of 168, okay? We think because of the ratio here, we have chlorine. So if we remove the chlorine on there, that's 168 minus 35, which should give us 133. And so that 133, our empirical starting formula, is going to be C10H13Cl1, okay? Now, because of our functional group here, we probably have an OH here. We have no other functional groups, and these all look like they're close to a heteroatom. I think we're looking at probably not a nitrogen, probably oxygen substitutions at this point. We have 1, 2, 3, 4, 5, 6 kinds of carbons. Okay. So, oh, my chat's hiding under the thing here. Okay, do you have a different book, Emma, than this one?
I have the 8th edition, but mine can look completely different.
Okay, because mine looks like something else as well. Oh, so these are the additional problems, the bonus problems. Oh, yours looks different too. Okay. Let me see if I have the ones that match this chapter then. The answer, those are bonus problems. It's 7. Those are solved problems. The 6 is multinuclear. Okay. So this is the digital version of the 8th edition that I have. I'm pulled up. I have their companion site. And so everybody has something different than what's here, or everybody has something different? Okay.
Yeah, mine is different too.
In the 8th edition that I have, it says assigned problems technically as opposed to additional problems. So
okay. I have the 7th edition, and mine's different as well. Okay, well, that's great. I will post the answers, by the way. I have the answers for this. So, well, I'll figure out the answers for this. Because in mine, so yeah, I have on my assigned problems, chapter 8, on my 8.1, it has a molecular ion peak of 112. Is that what you guys have? Okay, so that's consistent with number 7 here. Well, let's continue on with this since we've already done so much work on this. Okay, so we've identified our molecular starting peak. We've identified the fact we have chlorine. We have identified we probably have now that this is chlorine and that's an odd number, we probably have an OH here because it's broader. We have something that has everything is attached to a heteroatom, and it looks like there might even be an alcohol here because of this peak here. And we have 1, 2, 3, 4, 5 different types of carbon, 6 types of carbon. So if our initial molecular formula from the 133, which is the parent ion peak minus the chlorine, that gives us a C10H13. And if we substitute one oxygen, it's not enough because we have 1, 2, 3, 4, 2 oxygens. If we substitute 3 oxygens, we'll end up with C6H13O3Cl. Okay, now that's getting me to look like something I've seen this kind of structure before. And with this kind of structure, I've seen it look like let me pull up something I can write on here. Is that blank? Okay. That structure should look like, have any of you ever worked with polyethylene glycol or a PEG molecules or anything with these alternating ethers and ethyl groups? Okay, I'm going to share my iPad right here. Okay, so in the case of something like this, if we had something like this, it's going to give us this massive peak all around 3.5, and then the OH is going to be either on this side or this side, depending on the solvent. So this kind of structure here, this polyether kind of structure, is what's reminiscent of what we see here. However, we have something different because we have 6 different types of carbon in our system, and we have a chlorine. So I would like to say, I'm still sharing this, right? So I think it's going to be something on the order of that right there.
Who do you want to speak next or go away next?
4, 5, 6, C6H13O3Cl. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 1. So that's really kind of tricky on a thing in a book, on an exam. So I wouldn't do this on an exam, but that right there is reminiscent of this polyether, the polyether chain that you would see on this. Let me go back to the thing. All right, so you should see that Proton Nmr right here. See where that Proton Nmr has this large mass? This is all those CH2s next to those oxygens, and then this is the OH at the end. So I think that's consistent with this structure here. I'll look it up in the end and find out if we have it. All right. Questions on that? That one was harder than I was expecting for the first question in the set. So, okay. All right, well, let's move on to this version, chapter number 2, and see if we can't get an easier one. Okay. So again, we get chemical ionization plus the electron impact here. The chemical ionization shows a parent ion peak. A base peak at 113. So that's 113 minus 1 gives us a base peak of 112. Okay. So 112 is our base peak there. We have a fragmentation, 41, 55, 70, 81, 97. So we probably don't have an aromatic ring just based on the fragmentation pattern here. It might be some kind of straight chain because these seem to be clipping off fairly regularly. Let's look at the IR. We have nothing over 3,000, so it's all aliphatic. Yeah, it's not 27,000, but we do have a carbonyl peak here. So that's kind of good for us. We have a carbonyl peak. And so we have something there. So we know we need to do at least one oxygen substitution on our molecular formula. So let's start with that. 112. It's going to go in 8 times. So that's going to start with a C8. And then with a remainder of 8. So C8, H16 right there. And let's substitute 1 oxygen. So that's 16. So that's 1 carbon and 4 hydrogen. So that'll take us down to C7, H12O. So that might be a good place to start. Because we have a carbonyl, because of our molecular ion peak here, and because of this fragmentation pattern, let's start there, okay? Now let's go gain support with our system. Ooh, that's interesting. We have a peak up here above 9, okay? That's good, and if we blow that up, let's see, that looks like a 1 to 1 to 1 to 2 to more. That might be 3. So that might be 4. 2, 1, 1, and 1. All right. So what's the peak up above 9? It's a single. It's not split.
Aldehyde?
Probably an aldehyde. So let's look at the carbonyl. Carbonyl is a little on the low end, so that's pretty good for an aldehyde right here. And we do have this peak right here at 2,800. So that's usually 28 to 2,700 is where we get that aldehyde peak. So I think that's a pretty good guess right here. What about these peaks right here? Around 6 here. We don't have a tryptophan, we don't have a 77 or a 76, we don't have a 91, so we don't have a benzene ring. An alkene, yeah. But what's important about this alkene is that it's di-substituted. And so it is either cis or trans alkene because it looks like we have one hydrogen, one hydrogen, one hydrogen. Then we have two hydrogens, maybe four hydrogens, and maybe three hydrogens. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And right now, our empirical formula is C7H12O. Okay, so our integration on our Proton Nmr agrees with our assessment. Yeah, so one hydrogen on each of the carbons on that double bond. That's exactly right. Okay, so we have a substructure of that. So our substructure already looks like, let me pull up my iPad real quick. Share iPad. Okay. So based on what we have, based on just the mass spec, the parent ion peak, and the carbonyl compound, and the Proton Nmr, we have a C7H13O. This is supported by Proton Nmr integration. Our subgroups we also have are all aliphatic, H, and we have some kind of, I'm just going to draw it as cis right now, but we'll figure that out when we look at the Proton Nmr. So these are the fragments we have so far. So let's go on to the, back to this right here and see what else we see. Okay, so let's go on the carbon here. So again, we have something way up 190. We have one proton on it, odds up, evens down. And so if we look at our second line here, this is our 137 degree peak. And just fell off my pen. All right, so we have one here, we have 2, 2, 2, 2, and 1 or 3. So being that our Proton Nmr has this triplet here with a 3, I think we have at least a CH3 at the end of a chain, which is supported by the fact that this is just below 1, and we have one carbon that's that's 3. Now let's count our carbons. We have 1 carbon, 2 carbons, 3 carbons, 4, 5, 6, 7 carbons. And that's how many we're supposed to have. This is, of course, chloroform. One of the carbons has 1 hydrogen on it, and one of them looks to be quaternary. And these seem to be the alkene peaks here. So that's interesting that we have 2 up there. But we have, this is 2. So we have 2 peaks. So we have 2 peaks on 2 hydrogens on the same carbon in the alkene. So we don't have that cis or trans, we have a geminal, but they're different from each other. Okay, do we see that? We have 2 of these alkene peaks, but we only have 1 of these alkene carbons has 2 hydrogens on it. So that means we have a different substructure here. That means our substructure is not the cis alkene. It has to be that right there. And they have to be somehow different. So there has to be one group over here that's different than this group over here to make them different. So that's something to look into. All right. So let's go back and calculate our index of hydrogen deficiency. We have 7 carbons, we have 6 hydrogens. It's 12 hydrogens, so our hydrogen deficiency index is 1, and that's taken up by the aldehyde carbonyl. Did everybody get 1 for that? Terminal alkene, yeah, you got 2? We had C7H12. Oh, plus 1. Yeah. So 2. So we probably have a ring then. Yeah. So that would account for that exomethylene having different looks at it. But again, this one has no hydrogens on it, and this one has 2 hydrogens on it. So that's telling us something about the system as well.
Wouldn't the HDI of 2 just account for the carbonyl and the double bond?
Oh, you're right. And there's no ring. You're right. I forgot about the alkene there. So you have the alkene and the aldehyde are accounting for all of those systems. Okay. Now let's see what we can divine from this splitting patterns here. We have this, it looks like 2 hydrogens and 3 hydrogens. Let me see if I can blow this up again. Hang on, I'm sharing the wrong screen again. All right, if we look at this over here, let's see if I can move that up there, move this over here, and move. Let's see if I can't blow that up. See if we can see if that's a quartet or not. No, that looks like a triplet, and that looks like a triplet, and then these look like multiplets here. So something here is splitting this, and then this is only being split by 2 protons. It's weird that that would be 2 alkene, yeah. And then that's, okay. So that's the information we got from there. And that's all we have. We don't have any het core or anything like this. So we have 7 carbons. One's the carbonyl, 2 are alkenes, and 1, 2, 3, 4 are similar. And this is probably our terminal methyl group. So let's see what we can build.
I have a question about the carbonyl carbon.
Yes.
So why we are seeing the carbonyl carbon on the depth experiment on at 135 and 90 angle?
Right. Because, well, the 135 is because it has 1 hydrogen on it. So it makes the aldehyde.
Okay.
And
Yeah.
I'm not sure what angle this is. This is probably 60, which would also give things with just 1 hydrogen on them. Or what would give things
On CH only. It's
Yeah.
90. I think so.
Oh, you think it's 90? Yeah. So that would be the CH only.
Okay.
And so these
Okay.
would be the CHs. This is a CH2, CH2, CH2. So I think we have enough to build our structure now with everything we have. Let's go to, where's my screen share? Should be my iPad now. So I think we have something like, because of our thing, oh, there it is. We have something that looks, oops. So we have an aldehyde, and it has to be at the end of the chain, okay? Then we have a couple CH2s to account for. Then we have an exomethylene, exo like this, and there has to be more than one because we had no methyl group, just it wasn't split. So there has to be something like that. So we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 and 7. So that has to be the structure. And if we had a UV, oh, they can't be in conjugation because of the splitting on the system. So let's look at this again. All right, see how these are split like this? So that means this has to be a CH2 next to probably the carbonyl.
That's why we are back to this thing.
So
Was that question for me? So the fact that we have this is split into a triplet, which means it's next to two other hydrogens and it's high. So that's going to be the one next to the carbonyl. These two are split into multiplets, so we can't really tell. There might be a triplet, there might be not. This is definitely.
I think so. That is the overlapping of two multiplet. If you see can you go to the structure that you made on
Yeah.
your iPad? So we have 7 carbon.
Yeah.
If we make 3 carbon next to the alkene on one side.
Mm-hmm. So let's see. Did I count wrong? 1, 2, 3, 4, 5, 6, 7.
Like I'm asking about the terminal ethyl group. Instead of ethyl group, it might be propyl group. So multiplet can be created because of the middle carbon.
Oh, because of these two carbons here?
No, yes.
Okay. So what I think is that this is the peak, the higher peak at around 2.4 that split into a triplet. And then I think this one is the one that's slightly lower, but it's overlapping the other peak. I think these two peaks, this one right here and this one right here, are overlapping for 2 protons each. And then our last one here,
So there will be an effect of geminal hydrogen on these carbons.
not these right here would not be split by these geminal hydrogens. That's 4 bonds away. So there'd be 1, 2, 3.
If it's like that, then it should be like the second carbon should show only. Okay. Okay, now it makes sense. Thank you so much.
That second carbon has no hydrogens on it, according to the depth at 135. So that accounts for the one and no carbons on it. That accounts for those. And the fact that you have through space, there's probably some kind of hydrogen bonding or interaction with the carbonyl here. And this is just a methyl group over here. And that's why those two hydrogens are so split far apart. And the coupling constant for those is probably low, probably between 1 and 2 hertz, which means we might not see it. Wait, hold it. They did a blow up of that. Maybe there is something there. So they did a blow up, but no, this is those peaks there. So this is the multiplet here. This is the triplet here. And yeah, these are the 2 higher peaks here. So we do see some splitting here. They are being split, but the geminal coupling constant is so small that they look like singlets. Because remember, geminal and coupling constants are between 0 and 2, maybe 3.
How do you read the above one? Like, is there any short way to compare which peak belong to which peak?
Well, if you divide this number by 300, that'll tell you where it is on the ppm scale.
Okay. So
Because
is there any short way, like?
Yeah. Well, whatever megahertz NMR you have, you take the hertz you have divided by that bulk megahertz, the 300, and that gives you ppm always. So that's when these are listed as hertz, that's all you have to do. So for example, this one's right around just over 2 because
yes. Now I can understand. I divide the first 6 to 3, so it will be around 200 something.
Yeah, and so this is going to be, this is the multiple.
So 2, yeah.
They don't actually show the splitting here because it would be below 300 because it's below 1 ppm. So they do show the splitting on these geminal hydrogens though. So, all right, do we see how we got all the way to that and why? Notice that we knew that we had an alkene here, but we went to that geminal structure because of the depth experiment. Okay, that was the opener there, and the fact that we have this, we only have one with 3 on it and one with 1 on it, and the others had 2. But because of this complex splitting, we had to have that methyl group next to 2 CH2s to get to that triplet splitting at just below 1 ppm. That set the stage for we had an ethyl group we had the ethylene with the geminal hydrogens, then we had to have another ethyl group that was bonded to the carbonyl because of that splitting pattern and because of where all the hydrogens are. Okay. So, I mean, looking at this right away, I would have thought this was a cis or trans alkene, but by looking at that depth, you see that's definitely the geminal. Okay. All right, one more, and then we can go. And then on next week, we'll do reviews. We'll do like each chapter by themselves and what I'll be looking for. Okay. All right, anybody have any questions on this problem? Okay, maybe the next one will be easier. Haha. Okay, so let's see. Okay, I don't see any halogens. I see a pretty decent peak at 152. So I think that might be our parent ion peak. Divided by 13 is equal to, that starts with our empirical formula around 11 carbons. Let's see, 11 carbons. So that's 152 divided by 143, which gives us a difference of 9. So C11H 152 divided by 13. Yeah. 11 times 13. 143. Yeah, 9. So H20. So C11H20 is our empirical formula. We have a nice big peak at 91. Not familiar with a nice big peak at 91. Common fragment ions at 91 are C6H5CH2. So that's a long chain hydrocarbon. Might be a ring or a C. Yeah, because that's a pretty big peak there. 120 is a benzene ring with a carbonyl and an oxygen on it, and 152 is there. And then the next fragment is 53, which is a C4H5. Okay, so C11H20, I don't see us having that there. Let's see. We don't have the ratio to figure out how many carbons we have. All right, well, let's see how many carbons we have by looking at the carbon NMR. 1, 2, 3, 4, 5, 6, 7, 8 kinds of carbon. Okay. What does the carbon NMR also tell us?
Aromatic ring.
Right, we have not only an aromatic ring, but we have a di-substituted benzene. Because look at the depth experiment. These have 1s on them. This has 1 or 3. And we have 3 other peaks here that don't have hydrogens on it. So we probably have, gosh, that's a really low for a carbonyl unless it's an ester. Okay. But we have the possibility of that there. Oh, and we have a cozy too. We'll look at that later. So it looks like we definitely have an aromatic ring. Definitely probably 3 di-substituted because we have the hydrogens there.
The old one, yes, right.
Okay. So let's look at the IR here. We have definitely a peak above 3,000, maybe an aliphatic peak below 3,000. The only other thing we have here is this 1678. 1678.
So there is possibility of conjugation that decreases that value of carbonyl. Double bond with double bond, like aromatic ring, if it's directly connected to aromatic ring, the ester will goes down.
Right, especially esters and carboxylic acid salts. Those are the ones that shift further down.
Yeah, the backup and the passive backup, that's Yeah, that's the old stuff.
So that is probably pretty good. We have a peak way up here about 10. So that could tell us aldehyde or carboxylic acid. And we have a single peak down here. So let's see, 1, 2, 3,
This was all
4,
the way
5.
it was
7, 8.
So
It looks like we only have 8 hydrogens represented in our carbon, in our proton NMR. So let's get our, currently have C11H20. Let's get it down below that, do some substitutions. The first substitution I think we should do is maybe an oxygen to account for this carbonyl way down here. It's probably an ester or some conjugated ester right here. So that would give us 2 oxygens, right? So that'll take us down to C9, H minus 8 is going to be H12O2. Okay. Now let's go and look at the integration on the proton and try to get our how many protons we really have. We have 1, 2, 3, 4, 5, 6, 7, 8. So we're probably trying to get 8 hydrogens. So if we went down to C8, H8, O3, that would give us, let's see, something that could have an ester, something that could have an aromatic ring, something that could have a methoxy, maybe. It's kind of high for just a methyl group on a toluene, and maybe a carboxylic acid or maybe an aldehyde. I don't know. Now let's look at our carbons here. That would account for, this could definitely be the methoxy because we have an odd number of hydrogens here. So this could be 3 hydrogens, 1, 1, 1 hydrogen, and then these don't have hydrogens at all. So, so there's no hydrogen on that. So this could be a carboxylic acid, which would also account for this being so low. Okay. And it could be a carboxylic acid because the peak, this peak actually kind of comes down this way. If it was really dilute, we wouldn't see all that hydrogen bonding. Okay, so if that's true, if the C8H8O3 is our empirical formula, what is our hydrogen deficiency index? We have 8 minus 4 plus 1. Oxygens are neutral. I don't know, I usually get this wrong, so I don't want to say, but I got 5 too.
Yeah, me too.
Okay, so 5 would account for a benzene ring plus a carbonyl compound, right? So I think we have some fragments to build right now. So I'm going to pull up the iPad again and build a couple fragments for us. Okay, so just based on what we have here, and then we'll have to figure out exactly where which isomer we have, and we have a good way to do that actually. Okay, let's share my iPad. So what we have so far is
I was
we have
checking the .e, but there was nothing different. How we have that.
O3 as our empirical formula, which gives us our hydrogen deficiency index of 5, which gives us a benzene ring plus what looks like a carboxylic acid or a carboxylic acid salt, but it has to be conjugated. So it has to be attached directly to a benzene ring, I think, plus an OME. And I think it's the acid because of the peak in the Proton Nmr. And so we have some kind of di-substituted benzene. So that gives us 4 hydrogens on the benzene ring.
Nothing in the contact, not nothing in the contact.
This gives us 1, 2, 3 oxygens. This is 6 carbons, 7 carbons, 8 carbons. 1, 2, 4, 3, and then this is 3 hydrogens. So these fragments fit our empirical formula. these fragments fit our hydrogen deficiency index. But now we have to figure out exactly which isomer we have. And to do that, we're going to have to go to the Proton Nmr, I think. Oh, and we have cozy too. Good. So let's see what we have. So we have a cozy NMR. So this is the hydrogen to itself. So that means this, first let's look at the two N groups right here. The one at 4 is not attached to anything else. So that's consistent with being a methoxy group. It's isolated by itself. This is consistent with being the carboxylic acid peak here. And now we have our linear peak here. So we have our peak at, our lowest peak here at 7 is in between probably the one at 7.5 and the one at 8 because it's linked right here. Do we see that? So this is probably in between these two. So that's telling us we might have a meta substitution. And these two are linked together at those two higher. But notice that these two are definitely in correlation with the lowest number here, the lowest one. And then this high one. So, okay, so that's telling us something right there. Let's look at the cozy. I'm sorry, the other one. So the lowest one is associated with this one, that one, and the methoxy's over here, and that one's on an oxygen, so we don't see it. Right here, here, and here. So we definitely have those. We have 4 hydrogens hooked to 4 carbons on benzene ring, and we know exactly where they are. This is a quaternary carbon, and these are quaternary carbons here. So that being said, what isomer do we have? Okay, I agree with you 100% on that one. All right, so let's switch back to the iPad and draw the proposed structure, and then let's double check it. Okay, so our proposed structure is the meta. Okay, so let's go with the meta. And if we do on that side and OME on this side here, when we look at this, we have a total of 1, 2, 3, 4 hydrogens right here. So this one's going to be coupled to that one and that one. These two are going to be coupled. Well, yeah, so it's going to be coupled to both of those. We should have one that isn't coupled to anything, or only, oops, sorry, or only coupled through, let's see, that's 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds. So we should have one that's not coupled at all. And if we look back, we have that one. These are coupled. Which one's not? This is the middle one. It's coupled to 3 things. And then this is the one that's isolated. Is the one with the smallest coupling constant is probably the through ring coupling constant. So yeah, I think if we played with it a little bit more, we could identify each of the hydrogens to each of the, I mean, we can definitely do that here, but I definitely think we have that meta structure we were looking at. Okay. All right, questions on that, okay? So again, it's all about finding the evidence and refreshing the evidence as you go. Okay. So for our review, I'll go over things that, remind you things in each of the chapters. We'll start with chapter 1 and go through chapter 6, chapter 5. I will not have UV-Vis on the final. We've tested for that already. So I'm just going to have the individual chapters, mass spec, IR, proton and carbon NMR, and then we'll do the whole problems at the end. All right.
And also about the heteronuclear compound, you were saying that will also be noted.
Right. There'll be each of the chapters, each of the 5 major chapters will have their own page with questions about them, and then there'll be 3 full problems. Okay. So there's only 5 major chapters, right? Mass spec,
IR,
carbon, and multi
2D.
2D. Yeah.
Okay, not the hetero one. Not the hetero.
No, that's too hard on an exam. So, but when it comes to your research, definitely go back and look at the heteroatom stuff. But so it's going to be the 5 sets of questions just on the actual techniques themselves, not techniques, but the use of them, the techniques themselves, and then 3 problems that'll answer everything. Can we also do, yes, that is, the multi-bonds are harder, but yeah, we can do a multi-bond or 2 at that. I'll write it down. So in the multi-bonds, it's almost like you're looking at the proton splitting, where you see them starting to get all multiple split and kind of overlapping. That's where things like the multi-bond analysis, it's a little muddled. You have to do some sleuthing about it, but that's a good idea. We should do a couple problems on that.
Like in HMBC, how far the bond we see the interaction, like 1 bond, 2 bond, 3 bond, 4 bond, how far?
Most of the time it's 4, or it's set up to 4, but you can actually, with a pulse pattern, you can actually take away everything that's less than 4 or 5 or 6. But most of the time when we look at them in a book like this, it is set to 4 bonds. So you get that extra bond over. So you have your regular Proton Nmr, which gives you that 3 bond connection. And then the HMBC just gives you that next one over. And the next one over is what that's how you can identify, because from just your standard cozy, you're going to get the 3 bond. And then by adding the het core, you can like mark in where the cozies were. And then those next ones are the 4th bond. Okay. So that's how to look at that. The cozy complements the multi-bond correlation that way. Yeah. And it takes a long time to interpret, so it's not a great thing to do on an exam, but it's definitely for an activity that, and we did do at least 1 or 2, I think, when we were doing carbon multi-nuclear NMR. So, but all right, any other questions? Okay, I'll have to, maybe I have a strategy sheet on analyzing that. I'll look at it. I'll see what I have in my notes here. Okay, all right, I'm going to go ahead and stop recording.